Alright, so in this video I'm going to be explaining another approach for event extraction, which is about this model CLEVE, which is contrastive pre-training for event extraction. I have a playlist for contrastive learning so you can see the background. So I'm going to be focusing on this paper in 2021. Event extraction has considerably benefited from pre-trained language models by fine-tuning. However, existing pre-training methods have not involved modeling event characteristics, resulting in the development of EE models cannot take full advantage of large-scale unsupervised data. To this end, we propose CLEVE, a contrastive pre-training framework for EE, to better learn event knowledge from large unsupervised data and their semantic structures. AMR, for example, abstract meaning representation, obtained with automatic parsers. CLEVE contains a text encoder to learn event semantics and a graph encoder to learn event structures, respectively. Specifically, the text encoder learns event semantic representations by self-supervised contrastive learning to represent the words of the same events closer than those unrelated words. The graph encoder learns event structure representations by graph contrastive pre-training on parsed event-related semantic structures. For example, you see the AMR graph of that. And this is an example from this data set, which is very popular. And you see the event schema. For example, your event type, attack, has many argument roles, such as attacker. So you see the framework. First we have AMR parsing. Now that we have a graph, we can have a graph encoder. On the other hand, because of good initializations, we need this text encoder for good initialization. Then we have AMR subgraph discrimination, that showing, okay, this one goes together, so this is a good pair. For example, attack today, so this subgraph, this subtree, and there is another point is report attack today, this one, and report 01 attack. These are sample things. So you can either sample like this. So these have similarities, so we can use for this contrastive learning. But it doesn't have similarities with other things. Like, of course, this approach is memorizing, and because you can have different things seemingly unrelated, but they are in the same context, so it's very hard to identify that. CLEVE relies on AMR structures to build a broad and diverse self-supervision signals for learning event knowledge from large-scale unsupervised data. And we use automatic AMR parsers to parse sentences in unsupervised corpora in AMR into AMR structures. Each AMR structure is a directed acyclic graph with concepts as nodes and semantic relations as edges. Moreover, each node typically only corresponds to at most one word, and a multi-word entity will be represented as a list of nodes connected with name and edges. Considering pre-training entity representations will naturally benefits event argument extraction, we merge these lists into single node. Then we have this pre-trained language model and then because we want to have a text encoder as a good initialization of our graph neural network. And then to learn to discriminate the positive trigger argument pair from the negative pair, and so that model event semantics, we define the training objective for a positive pair as a cross-entropy loss of classifying the positive pair correctly. We adopt the cross-entropy loss here since it is more effective than other contrastive loss forms. Then we obtain the overall training objective for event semantic pre-training by summing up the losses for all positive pairs of all sentences in the mini-batch. In CLEVE, we utilize a GNN to encode the AMR subgraph to extract the event structure information of the text. Given a graph, the graph encoder represents it with an graph embedding. So CLEVE is agnostic to specific model architectures of graph encoder. And they used this graph isomorphism network for their graph neural network for graph encoder. And then they use AMR subgraph discrimination because to learn transferable event structure representation, we designed the AMR subgraph discrimination for event structure pre-training. The basic idea is to learn similar representation for the subgraph sampled from the same AMR graph by discriminating them from subgraphs sampled from other AMR graphs. Given a batch of AMR graph, each graph corresponds to a sentence in the unsupervised corpora. For the ICE graph, we randomly sample two subgraphs from it to get a positive pair. And all the subgraphs sampled from other AMR graphs in the mini-batch serve as negative sample. So like in figure 2, the two green subgraphs are a positive pair, while the other two subgraphs sampled from the purple graph are negative samples. And similar to event semantic pre-training, we adopt the graph encoder to represent the samples and define the training objective like this. So in the supervised setting, they adopt dynamic multi-pooling mechanism for text encoder. And the dataset is just this popular ACE25 dataset because it contains 599 documents and 33 types, 35 argument rows. For the baseline, as I said, they need a text encoder to initialize the graph neural network. So the name of that text encoder is it is using this model, Roberta. And then you see the phone score for CLEVE is just 50%. Of course, this is the unsupervised event extraction performance. For the supervised results, a phone score is, for example, 61. In 2020 is 61. For CLEVE, the for EAE is 34%. You see that first of all, CLEVE is much better than BioLSTM CRF, better F1 score. It is also a little bit better than Roberta, as you see, a little bit. So you see, the improvement due to contrastive learning is just very small. So for joint constraint clustering algorithm, we get trigger candidate set, and then we cluster with spectral clustering algorithm that I've explained in a video.